Is it okay? So that's the definition. And now this is for general real order. We define this for a general real order nu. Now we need to because our goal is to define a second solution for integer order, so we need to take the limit for the nu goes to integer. So let's even something. We need some space to write down. So for integer n, y sub n, we need to take the limit of n. Nu goes to n, and integer n. So n is integer, and y sub nu, which is given by this, defined by this one. Right, just plug in this into this and take the limit that nu goes to n integer. But in this limit, both the numerator and denominator are 0. So that suggests us to do a derivative of that. The derivative of both the numerator and the denominator, right? And the denominator derivative is straightforward. It's just cosine pi nu multiplied by pi, right? So the numerator is easy, and so that is give you everything. This, for the first term is fine. You cancel the cosine pi nu with the derivative of cosine pi nu, right? And so that one is fine. And let's see. Cosine pi nu, so this. I should actually, I mean, maybe just write out explicitly pi cosine pi nu. Right, that's the derivative of the denominator, and the numerator has the first term has two parts. One is derivative of the cosine, which is minus pi sine pi nu, which is turned out to be unimportant because when that nu goes to n, and after the derivative, so that one will be 0. Sub nu, right? And then the other is cosine pi nu dj nu. Now we take the derivative over the order, not the argument. Okay, so to be a little careful, right? And then that's the second. That's the first term, and the second term is just dd nu of j sub minus nu. Okay, so that's all the derivative. And so after that, we set the nu equals to n. That will kill this term. And cosine pi nu is our minus 1 to the n. Oh, right. But for the first term, we cancel. Okay, for the first term, we cancel. So, just keep writing. The first term just cancel. So you have a wonderful pi out. Cosine term cancel. So d nu, dj sub nu d nu, and then it's for this one you have this minus 1 to the n. D nu, j sub minus nu. Okay, so that is how much time do I have? 20 minutes. Right, that should be the last discussion. I mean, not exactly the last, but the most of the discussion is you have the time to do the derivative. I mean, this is a little bit long, but we take the derivative, but the idea is we have everything we need to take this derivative. We know how to take the derivative of this power series, right? And because we have learned how to take the derivative of gamma function, so that's one of the sections. We define the digamma function, so that we know how to take the derivative of the gamma function, so that that is useful in this situation. Okay, so and then the idea is we finally get the expansion for y sub n, which is more complicated than this one. The main feature is to show that all these j sub n are singular near x equals 0. And you want to know from the form of the expansion the property of the singularity, what is it proportional to for different order. You want to look at the singularity, and the singularity is actually coming from this derivative. Mainly is the second term. So there's some usefulness to actually carry out the derivative and see how this singularity is coming from. Let's see if we have time to finish this. Right. So we can use the power series to do the derivative. So we consider this to the sub nu, the nu. No, we just need to do it term by term, right? And now the new dependency has you have the new dependency in the power of this x over 2 factor, and then the new in the gamma function. For this factor is slightly easier. It's the derivative of a function to that power with derivative over that power, right? And that is basically is the same. It's like the exponential function, right? It's like the exponential, keeping the same form, but take the log of the argument. So instead of log e, will give you 1 is a log of x over 2, right? So it's writing the same exponential function, and then log of x over 2, right? And then take the derivative over the argument of the exponential function out of the power function. But that is just 1 because you have nu here, so that's just multiplied by 1. Right? So that's the first term. I mean, take the derivative over this dependency. You give you this one. It's okay. So this one is easy, right? And for this one, is also have a property that other than this x over 2 log of x over 2 factor, everything else is just going back to this original power series. So this part is just j sub nu. Okay, so that one is nice form for this one. Okay, so that is the first dependency. The second dependency is this gamma function. So we need to use the digamma function now. We have -1 to the s power. We have x over 2, the nu plus s, and the actually so this is nu equals n. Okay, and now the derivative of gamma function. Now we remember that the definition of the digamma function psi z is dz of log c. Remember log of gamma z, right? Because we wanted to avoid this infinite power by taking the log first and make it a summation. Right? And so that is just 1 over gamma z, d gamma z, dz, right? So now we need the d dz of 1 over gamma z, right? Because this is in the denominator, so that is minus gamma square nu square d gamma dz. And d gamma dz is psi multiplied by gamma z. It's minus psi d gamma z. It's okay. So I got everything right, right? So we only need that. So all together is let's take a derivative of that, and it becomes sine of nu plus s plus 1 divided by gamma nu plus s plus 1, right? And then there's a negative sign. You can, if you like, you can write out the negative sign, or you can add to that power, but that doesn't matter. Write it out. Okay, so that's this term, right? And now by this, in this derivative, we are assuming nu is positive, because finally we knew that nu equals to n, which is defined as a positive integer. Assuming this is nu is positive, and then finally nu goes to integer, positive integer, and sum over s from 0 to infinity. And we see that all these gamma functions are finite. Right? There's not singular. You don't get 0 or negative integer here, because the smallest one is n plus 1, and n is positive or 0, right? So at least 1. You have at least gamma 1 in the denominator, so that is non-singular. And you look back at the property of the digamma function. This is also regular, and so this the first derivative actually give you everything regular. Okay, so that's straightforward. And again, you can say that this is just this nu. And now we have we need to take this one, and dj minus nu and d nu, and so what we need to do is just changing nu to minus nu here, right? And there's some changes. Did I miss a nu here? No, that's derivative is actually just take this. Right, that's fine. So the only thing is the power function now is at minus nu here, right? Because we have dd nu and change nu to the minus nu in this vector. So that's a minus nu. We take the exponential function, power function, we get log x over 2 the base, but then we still need to take a derivative over that. And so there's a minus nu, d minus nu, d nu is give you minus 1. So there's a minus factor here. And so the first term must be minus j minus nu log x over 2. Okay, so that is similar to this one, but except this minus negative factor. Right? So that's one difference. The second one is now you take the derivative over the gamma function, everything the same. You can use everything the same, except you change nu to minus nu. Right? This nu change to minus nu. Right? I think that. Say that again. Yeah. Right. Oh yeah. And it seems like everything the same, right? Except that nu goes to minus nu. I suppose this negative sign is coming from here. So minus minus 1 to the s plus s factorial. Everything still the same. X over 2. And you have minus nu plus s. Change nu to minus nu. Nu to the minus nu. Nu plus 2s, right? I miss all of that. Nu plus 2s. Nu plus s. Nu plus 2s. Right? Yeah. And then psi minus mu plus s plus 1 divided by gamma minus nu plus s plus 1. Right. Now again, the first one is fine, just multiply by log x, so using the same function. And as the second term will give you some singularity. So especially when nu goes to minus n. So if nu equals minus n, right, and actually nu equals minus n is the original nu. So this nu becomes n, right? We already take the minus sign. So nu becomes n is positive. Then from s going from 0 to infinity, so somewhere along the line, s is I should say is up to a certain integer of s, all these will be singular because you have a negative integer, so minus n plus s plus 1, right? But then you have this diagonal function here also, and the idea is that you see that both are singular at negative integer, and so we can take the ratio of these two and get a final result. So hopefully, and so now the final step is just taking this one, this one, and when both are singular at the certain location, what do you do? You can take the derivative, but another way to do it is use because you see that both are symbol pole and of the same order, right? We can actually just take the ratio of the residue, because the largest term as nu goes to an integer, like nu goes to n, is the singular term, the most singular term, the pole term, so the residue divided by the singular argument, and both will have the same, so you same order of the singularity, so the singularity cancel, and in this case it's a symbol pole, so it's just a first order pole, right? And then just take the ratio of the residue will be fine, right? And so this term will be equals to, now the residue of the gamma function is, we mentioned that, I don't know whether we did actually divide that. It's actually fairly simple to divide that, but let's just look that up. The residue in, that is equation 13.29. Okay. So this is the ratio, this is the residue of, if nu is equals to n, right? Or we can say this way here, residue of gamma minus n is equals to minus 1n over n factorial, right? Now this for the, I should actually say, because some of them are negative, some of them are positive. For the negative, this is for minus n plus s plus 1 smaller equals to 0. we take the residue, and that this you compare with that the root of the gamma function is minus n minus s minus 1, right? So that becomes n minus s minus 1 factorial, right? And then minus 1 to this n, so minus n minus s minus 1. So that's the residue of the gamma function, right? And then for the digamma function, you can work this out a little bit. That is in, should be 13.2, section 13.2. Just need to look up the equation. So I have some space here. I already did this. The digamma function, 15.38. The digamma function is psi z plus 1 is equals to minus gamma plus sum over n over 2 over m. Okay, so for integer, for a negative integer, so it's summing for m from 1 to infinity, right? So, somewhere along that, if z is a negative integer, or including minus 1 for this case, because that includes z, this is includes 0, just like the gamma function including 0 or negative integer. So for this case, the residue is basically substitute whatever z is equals to, like z plus 1 equals to a minus integer, right? You see, the m, the singularity is at when m equals to m plus z equals to m minus n minus 1, right? And so when m equals to n plus 1, right? And that will be singular, but then the same z is n plus 1 minus n plus 1, right? And so m is equals to, if this is equal to 0, the m is n plus 1, right? M is n plus 1, then that will make it singular if z equals that, right? And c is equals to minus n minus 1. The m is equals to n plus 1. The residue is minus 1, right? So the residue, right? Let's take the ratio because c is changing to n minus 1 here, but singular at m equals n plus 1. So it's to cancel to a minus 1, right? And that's the coefficient of this 1 over z minus n, right? Or z minus n minus 1 factor in the denominator. So that the residue of the digamma function is just minus 1, right? Okay, so anyway, so that is so that will give you a finite result. So we actually wanted to show that will give you a finite result, and so therefore, and then for the s is above this, so this is s is less than or S, this is S is less or equals to n minus 1. For S greater than, for S greater or equals to n, then you have everything is regular because psi and gamma at those S are regular. Okay, and so we have two terms. One is when these are singular, and then you get the ratio using the ratio of the residue. And then finally, you have has summation S is starting from n to infinity, and everything else in this series, that series is regular. Okay, and so maybe it's this sum over, just write. I'm just right at time, so probably I cannot totally finish it, but just to sketch the idea. Just so you have one term is some S from 0 to minus 1. And then you have minus 1 to the S power, S factorial, x over 2 minus mu minus 2S. And then whatever this ratio, you can actually use minus 1 to cancel that. You have minus 1 to the n minus S power. You have another factorial minus n minus 1 factorial. Right, that is this ratio, and then another series. Now it's S is from n to infinity. Everything else the same. Minus mu. This is a little bit tedious, long derivation. So you have this factor and that factor in this term. And the final trick is to shift is all this S. That's just like what we did for to get to this j to the minus n. We did this shift before because the power series actually starts from n to infinity, but we shift it back to 0 to infinity, and there will be some movement of this or this S in the dependency, and actually it turns out that this term will be very similar to this one, except that the gamma, the psi function will be shifted a little bit, and then finally combine them using this, combine these two, this one and that one. And we won't have time to do that, but just compare with your textbook, just over time a little bit, but just discuss the property in third. The final result is in 14.61. If you look at 14.61, the first term is the regular log j sub n. This one times the log x over 2. And the reason that this two actually combine because you have a negative sign and you have negative 1 to the n power. But j sub n and j sub minus n are related to this minus 1 to the n power. And this negative and negative cancel. So you get actually two of them the same. So this combining this term and that term give you the first term in 14.61, right? The second term in 14.61 is coming from this term. This term is summing from S from, in that case, it changed the case. It doesn't matter. From 0 to n minus 1, the summation, right? And then you have all these x to, in that case, minus n plus 2s. Plus 2s. Yeah, plus 2s power. And then all you have this, but that is the second term. And I may have the residue actually is going to it divided by the residue. This is the residue, right? Divided by the residue, so this actually. And minus S minus 1. And minus S. Yeah, when you take the ratio, the residue is divided by this residue to add the power, the factorial going in the numerator. Okay, so this factorial divided by that factorial, this. So we get this most important thing. This is x to the minus n power when nu goes to n, and the rest are regular. This series and that series combined with the third term and 14 from 61. One is this psi. One is this psi function. The other is this function. But after you shift the S, the summation index, but now we can see all the properties. Singularity is you have the log x term is singular at x equals 0. You have x to the power minus n is all singular. So except when nu equals 0. When nu equals 0, you're summing over 0 to minus 1, which means that you don't have this term. For nu equals 0 or the y sub 0, you don't have the second term. You only have the log term. Okay, and for y to the minus n, the most singular term is this x to the minus n power. So change nu equals n. So the property of the singularity is given by this term, right? And then the rest are just regular summation. So okay. I skipped some part, but then we get most of that done. So you should have most of what you need for the exercise for the homework for this week. All right, but I'm out of time. All right, so I'll stop here.